Hello, and thank you for attending our presentation, Flow Label, Exploiting IPv6 Flow Label. I'm Jonathan Berger, and this is a joint work with Amit Klein and Professor Benny Pincus from Bar-Ilan University. Let's begin with a short introduction of IPv6. IPv6 is the latest Internet protocol and it was introduced in 1998. It has seen many changes since then and became an Internet standard in 2017. One of the catalysts toward the IPv6 transition is that the IPv4 address pool has run out. All of the IPv4 addresses pool of the regional registers, such as RIPE, have already been allocated to the ISPs. But what is the current adoption state of IPv6? So, we are talking about 30% worldwide adoption, even some countries with almost 50% IPv6 connectivities, and these numbers are increasing. Now, an important note is that all modern operating systems support the IPv6 protocol, and furthermore, for cases that a client with an IPv6 connectivity attempts to connect to a server that supports both IPv4 and IPv6, IPv6 would be preferred by these operating systems. This means that users might be using IPv6 unknowingly. The IPv6 address size. One of the changes IPv6 introduced is a 128-bit address. This address is composed from the high 64 bits, which are called the network prefix, and are usually assigned by the ISP, and the lower 64 bits, which are called the interface identifier. These lower 64 bits are generated by the client's computer to form the 128-bit address. The IPv6 temporary addresses. IPv6 has also introduced a privacy extension mechanism which is implemented by all major operating systems. This mechanism's goal is to prevent tracking of users merely by their IPv6 address. In order to prevent such tracking methods, IPv6 has introduced something called a temporary address. This address is used for outbound traffic such as internet connections. These temporary addresses are regenerated every certain interval, which is usually 24 hours, and it is done by generating a new random interface identifier. Now, here is a comparison between IPv4 and IPv6 headers. We can see that IPv6 has a constant size header, and some of the optional headers of IPv4 were moved to the IPv6 extension headers and are not part of the IPv6 header. In addition, IPv6 has also introduced a new 20-bit field named Flow label, which is the focus of our work. Okay, so a bit of flow classification and the flow label. A flow is defined as a sequence of packets sent from a particular source to a particular destination. The flow classification is usually done by forwarding devices such as routers or load distributors, and it is traditionally based on the five-tuple of source address, destination address, source port, destination port, and protocol number. But this might be problematic when the forwarding devices are not aware of some of the five-tuple fields, for example due to encryption or fragmentation. So to overcome this issue, IPv6 has introduced the flow label field that together with the source address and the destination address should provide forwarding devices the ability to perform an efficient flow classification. The flow label specification RFC recommends that the flow label value should be uniformly distributed and based either on a hash function or a PRNG. And starting with Windows 10 version 17.03 and Linux kernel 4.3, the flow label is populated with non-zero values. In other words, these kernels implement a flow label generation logic. So how do they implement the flow label generation logic? So, in Windows 10, they use a hash function for TCP and UDP traffic, while for Linux and Android, the flow label for TCP connection is based on PRNG, and for the stateless protocols, such as UDP, it is based on a hash function. Let's begin with Windows. We reverse engineered the TCP IP driver, and we found out that the algorithm is based on a toplets hash with a 320-bit key on the destination address, source address, destination port, and source port. This 32-bit hash output is then truncated to feed the 20 bits of the flow label. An important observation is that the key k of the toplets hash is a static 320-bit key that is regenerated only on system reboot. And note that in Windows 10, shutdown and startup does not equal to reboot due to the fast startup feature of Windows. so the key won't change if you shut down and start up your machine. Another important note is that the toplets hash is a bilinear function, and this is how it's defined. Now for Linux and Android. For Linux and Android, we focused on the hash function logic, which is relevant for the stateless protocols such as UDP. In Linux and Android, the algorithm is based on a hash input that is based on the traditional 5-tuple. The hash function being used is the Jenkins hash function, and a very important observation is that the key for the hash function is a 32-bit static key that is regenerated only on system reboot. This is the detailed algorithm, and the further analysis appears in the paper. Now, for the attack concept. All the hash input values of the algorithms we have just seen are attacker observable values. Both Windows for TCP and UDP and Linux and Android for stateless protocols use a static key. So this key, or parts of it, might be used as a device ID. Furthermore, the key is regenerated only on restart. And because this key is static, a device ID based on this key would be the same device ID across browsers, regardless of network switches or temporary address renewals. These conditions make it perfect for device tracking. Interestingly, this concept also allows an attacker to carry passive tracking, which we will describe later. Okay, so let's sum it up. From the cryptanalysis of the flow label generation algorithms, we got that they are based on hash functions, which are based on attacker observable values, and use a static key that is regenerated only at startup. And this allows us to generate a device ID that is based on extracting the hash key, or parts of it, that can be then used for tracking devices. Now, let's present the attackers. We begin with the active attacker. This attack is based on an HTML snippet that can be embedded by any third-party site. This snippet forces the target to emit IPv6 traffic to the tracking server, and the result is a consistent device ID regardless of the browser used, network changes, or temporary address renewal. This attack requires just 3 UDP packets for Linux or Android and 5 UDP packets for Windows, or 9 TCP packets for Windows. Let's begin with the Windows UDP case. Recall that the flow label generation is based on the bilinear toplets hash, which is defined as follows. Because it's bilinear, taking some two equal size inputs gives us the following result. The XOR of toplets hashes of two equal size inputs is the same as the toplets hash on the XOR of the inputs. Here we can see that it holds due to the linearity of the toplets hash. Now, what happens if we set the XOR of these two equal size inputs to be 1 followed by zeros? We get that this is the same as a toplets hash on 1 followed by zeros, which results, by definition, to the key bits as follows. Here we can see that it follows by definition by just setting the input to be 1 followed by zeros. But this is a trivial leak of the key bits. So let's form the UDP tracking method. Recall the Windows flow label generation algorithm. The hash input is known to the tracker. Now, the idea is to achieve a trivial leak. So, we would like that the XOR of hash input values from two different packets would result in a single 1-bit. Assuming the common case of a single source address, the XOR of the source addresses would be 0. If WebRTC is used to emit the UDP traffic, it would cause all the packets to originate from the same source port, which would result in a XOR of 0 for the source ports. This leaves us with the destination address and destination port, which are controlled by the tracker. So, the tracker can set these values to achieve a trivial leak. But note that depending on the choice of the tracker can leak different offsets of the key bits. Therefore, by controlling these fields, the attacker can achieve multiple trivial leaks and leak multiple key bits. This results in more than 80 key bits as a device ID. Note that this attack didn't require the attacker to know the values of the source address or source port. This allows the attacker also to track users over VPN. What about generic cases, such as TCP or different source ports? So, we can exploit the linearity of the toplet's hash and yield linear equations on the flow label values because the hash input fields are known to the tracker. The solution of the equations is the key bits used to generate the flow label, and they would serve as the device ID. We showed that by specific choice of the least significant 64 bits of the destination address and using the same destination port, it is possible to derive an 80-bit device ID by triggering just 9 packets. Now, let's see the active attacker for Linux and Android. Here is just a reminder on how the flow label is generated on these platforms. Remember that the key of the hash function is just 32 bits, so we can just enumerate over all the possible keys. Let's see how it actually works. The tracker triggers UDP traffic using WebRTC. The 5 tuple is known to the tracker, so the tracker can just mimic the flow label algorithm and enumerate over the 32-bit key. Once the key is found, this key would be the device ID. Note that because the flow label is a 20-bit truncation, at least 2 packets are required. Another possible attacker model is a passive attacker. This attacker is only able to inspect packets and doesn't have the ability to trigger specific traffic from the client. One example could be a server that just inspects its usual IPv6 traffic with a client, or a forwarding device that acts as an eavesdropping man-in-the-middle attacker. We showed that it is possible to generate a device ID by just passively inspecting IPv6 traffic. And again, because the generated device ID would be based on the static hash key, we get a consistent device ID regardless of browser use, network changes, or temporary address renewals. In addition, this method may also allow retroactive correlation of devices and their activity. So, from the bird's eye view, how is this attack work? The attacker begins with collecting or inspecting previously collected IPv6 traffic. For Windows, the attacker yields equations on the key bits that exploit the linearity of the toplet's hash to generate a device ID, similarly to the generic case in the active attacker model. And for Linux and Android, the attacker does the same as in the active attacker model, just enumerate over the key and use the key as a device ID. Note that there is no need to manipulate or intervene with the client's traffic, and there is no need to cause the device to emit specific crafted packets. This means that any forwarding node that is aware of the source address, destination address, source port, and destination port values, and is capable of dumping these packets, is able to generate a device ID and correlate the user's traffic. Affected platforms of these attacks are Windows 10 versions 1703 till 1903, and it was fixed in November's 2019 security update. For Linux and Android, Linux kernels 4.3 till 5.3.9 are vulnerable, and the fix was to move to the SIP hash with a 128-bit key. Conclusions. We saw that it is possible to track Windows and Linux and Android devices by inspecting the flow label values, either by active triggering or by just passive inspection. This was tested successfully over 19 different networks worldwide and including VPNs. We also witnessed how attacker observable values, even if they are not security sensitive, might be misused. We conclude with the recommendation that vendors should always use industrial strength crypto together with an educate key size when such observable values are involved. We finish with a short video demo. The demo shows that for different browser choices, our HTML snippet generates the same device ID for the tested device. Thank you very much.